Okay, thank you. Well, I realise I'm the last person to speak, so there's a bar that we need to get to over there, so I'll try and keep this brief. As I said, this is looking at how CFD results can influence pedestrian analysis and evacuation results. My co-conspirators are at the bottom, and this was done in conjunction with these guys who are based in the UK. So what I'm going to explore here is just what happens when you start putting CFD, here FDS results, into pedestrian modelling software such as STEPS. It's applicable to any situation really, but this is a road tunnel, and I would have liked to have shown a specific case study, but most of the case studies we're working on at the minute are confidential, so this is kind of a hybrid. So the actual specific example it's credible, but it's not necessarily specific, so don't ask too many specific questions. But what we're looking at are temperature, heat flux, the fractional effective dosage of carbon monoxide and visibility, and considering whether basically the tunnel environment is tenable for evacuation. And I think one of the questions that I've been asked in the past is, why would you model a road tunnel? It's a straight line or a line with a little curve. You can consider how quickly people move and put in a pre-evacuation time. You can sort of do this by hand. And I think this hopefully will explain why you might think otherwise. So the example that I'm working with is a bi-directional road tunnel, as you can tell from my strong accent. Although I work in the New York office, I'm actually from the UK, so the cars are driving on the correct side of the road in this tunnel. And we can see we've got the tunnel is 416 metres long, 9.5 metres wide, 5.5 metres tall. We've got a fire. If I can figure it out. The fire is right there. The fire is just there in the middle. I probably won't keep pointing. But this indicates all the different types of vehicles that were in there. For this study, we've taken the cross-section of cars and vehicles that were in there that were recorded for one of the tunnels we were working on. And each of them have their different occupancies. And I put a little star in. This represents the longest time to egress. It's the rear of the bus or coach nearest to the fire on either side. There's a 30 megawatt fire. It's got a slight slope up to the left, so the left-hand side is open, and both ends are open to the atmosphere. Now, I'm not an FDS expert, so please don't grill me on this aspect. That was what the guys in the UK did, but it's a point-extract system. There are 4.5 by 2 metre openings in the ceiling, 25 metre intervals. The 3 in the vicinity of the fire open. And we considered 2 cases, one which was 120 metre cubed per second total extraction rate, and one which is 180 metres cubed per second. So that's the FDS side of things. I think actually really quite well linked to what we were discussing earlier. There are obviously different ways of implementing pre-movement time. So for the study, one of the studies that we did, we basically said, look, there are different ways of implementing pre-movement time. So this paper we look at 2. We've got a fixed 5-minute for everyone in the tunnel. But then there's another approach that we were looking at. Well, okay, it's going to be variable, probably dependent on where you are near the fire, how close you are to the fire. So we instigated these pre-movement times, probability densities, at these different ranges, 0 to 50, 50 to 100, greater than 100 metres. And you can see we've varied it along with distance. Similarly, we have the same with walking speeds. As we said earlier, walking speed isn't a fixed. No one all walks along at 1 metre per second if they're able-bodied, and 0.5 metres per second if they're a person of restricted mobility. However, we've put that in as a sort of a standard case. We've also put in a distribution of walking speeds ranging from 0.5 to 1.5 metres per second with a 1 metre per second mode, roughly is based on NFPA 502. So what's interesting, and this is just sort of skipping ahead slightly to the results, but what's interesting on the difference between the fixed and the distribution is this is the 120 metre cubed per second fan case at 7 minutes, and we've had 46 people leaving, and you can see we've got most of the vehicles up in the distance here are empty, and in fact everyone's in the roadway and they're walking along like they're on some kind of marching outing. This is actually the same case with the distributed walking speeds and pre-movement time, and actually at the same time, instead of 46 people having left, we've actually only had 5 people have evacuated, and you can see there are still far more people in the coach up the front, and it's much more distributed. So how we do this is we take the visibility or the extinction coefficient into STEPS, and we use that to modify the walking speeds using the Jin and Yamada curve. But we could have used any curve, but this is the curve that we decided to use. So let's look at how we assess tenability. So the FDS results are all taken on a slice plane 2.5 meters above the ground, and in the case of heat flux facing up towards the hot gas. So NFPA 502 states that air temperature should not exceed 60 degrees Celsius. Heat flux, radiant heat flux should be no more than about 2.5 kilowatts. Visibility we take into account, as I said earlier, by affecting the walking speed, so that's sort of automatically taken into account in steps. And then we look at carbon monoxide and the fractional effective dosage. And this is essentially an equation that the ISO standard gives, which is accumulating the fractional effective dosage that the person experienced between the time, start time and their total evacuation time. And the effect is cumulative. And what I think is important to know about this is the way that it's set. An FED of 1 means that 50% of the population finds the environment completely tenable and 50% don't. And then obviously within that you can start putting different, well, what criteria should we use? Should we use 0.3, which then takes that down to only 11% finds it untenable? And I think 0.1 takes it down to like 1%. But anyway, the effect is cumulative. So the results. I'm going to quickly look at what the difference between the fan sizes, and I'll get into some of the more specifics. So what we're looking at here is we've got the 10-meter ISO surface visible. We've got the fire as that red blob there. You can see the 3 openings here, and you can see the people walking through the smoke. This is with a fixed pre-movement time and the case of 120 meters cubic per second. Oh, and of course, on the ground is projected the extinction coefficient. So we can see here we've got roughly 46 people have left. Now we've increased the fan size to 180 and significantly more people have left at this same time. This is up to 79 meters per second. 79 people having already left. So let's look at the different criteria quickly. So this is directly, these are plots from FDS. I've just taken it T1, 1 minute at the top and 20 minutes at the bottom, and broken it down into these sections. And the fire location is right in the middle. So we can see in this case, this is the lower fan speed, that things on the left-hand side here begin to get a bit untenable, or basically are untenable, with red being 60 degrees Celsius, untenable somewhere around the 5 to 6 minute mark. On the right-hand side, the area is actually much more contained. Obviously, there's a slope up this way, which makes a difference. And then realistically, most of this area remains pretty much tenable all the way through. We look at what happens when we increase the fan size, and you can see it keeps it much more contained. What I found interesting was actually this area becomes untenable quicker, but it's more contained. And actually it transpires that temperature was the limiting factor in this case. Again, that was straight from FDS. We did a look at the heat flux again, looked at the output from FDS, and I should point out that this is heat flux in only areas where people are present. Obviously what's going on in the fire is something else, and we're working on the assumption that no one's actually walking straight into the fire. And we can see that these are all nicely below the 2.5 kilowatts per meter squared. So this then, I think, actually answers really the question as to why you would bother doing CFD and then pedestrian analysis on essentially what is a straight tunnel. So we did a static calculation, just a hand calculation. You can work out, you've got the walking speeds. And we came up with a figure of about 15 minutes, 30 seconds. We can see now the difference. So if we've got the fixed scenario, which is the most analogous, we're adding about 13%. These statistics here are not necessarily particularly important per se, but what we can see is that the increase in fan size decreases that significantly. But what I think is more interesting is as soon as you've started adding in the distribution, the 2 fan sizes, if you just look at the total evacuation of all the people, you could say, well, what's really the difference? You've introduced so many variables, people walking and moving at different speeds. So what then you need to really look at is something like steps where you can look at the individual agents. This is now looking at the path of selected agents. And what we've got is time going up here, distance along the tunnel. So this is one exit, this is another exit, and we've got the fire essentially in the middle here. Now this is with a fixed pre-movement time, so no one you can see is moving here. And what we can see is that this over here, this actually corresponds to the person which I'll come on to later has the worst fractional effective dosage. is this person of restricted mobility getting out of a coach at the end. But what you can really see is the significant effect of the smoke on the walking speed. So obviously they're static here, walk to the front of the coach. They're walking more slowly until they're out of smoke, and then they walk much quicker. So this you can really visually see the effects of smoke on walking speed. And now we've got this, we can then compare that to what happens when we increase the fan size. So what you can see is, whilst actually the overall rate does come down a bit, when you start looking at these specific people here, they actually start, we can see they walk out of smoke a lot more quickly. So if I just flick back between the two, you can see that we're actually bringing people down out a lot more quickly. I should also point out that actually, going back to what we were discussing earlier, the overall metrics in the tables are based on 5 runs, whereas obviously these graphs are actually based on just one specific. So what you see in here is possibly not necessarily the case that will always happen. You're better looking at the averages. And then obviously, whoops, gone too far, yeah. Then when you start looking at the distributions, you realize, well, it's pretty much all over the place. People start moving at all sorts of different times, and hence you get this, the yellow represents the sort of the last evacuee out on each side. And actually also you can see the worst FED was in here, this person here. But again, you can, by looking at this sort of approach, you can see that the effect is there. People are actually walking out quicker, but obviously what's being masked is we just have to look at this person who doesn't leave until, well, he doesn't start moving until nearly the end of the simulation, or pretty much the end of the simulation, at which point he walks out completely unaffected. So that's sort of the impact of distributions. And then throughout this simulation, what we can do is, because we've got the carbon monoxide information in there, which we've again taken at 2.5 meter, put it in there, the individual agents, every agent goes through and records the amount of, or the percentage of carbon dioxide that they ingest, essentially. And at the end of it, we can come up with the FED. Now, actually, in this case, we seemingly came out well below any, I mean, this, if we say that 0.1 is about 1% of the population getting affected, then obviously this is a very low number. However, obviously it's worth saying that it's all statistical, so that doesn't mean that this person doesn't have issues. It just means statistically they're extremely unlikely. But what's also interesting is when you start, again, looking at the distribution versus distribution as opposed to the fixed versus fixed. The distribution case, we only get a reduction in FED, maximum FED. We calculated the average as well, but the maximum FED by only 10%. You actually start looking at this here in the fixed case where you're comparing apples with apples. You can see there's a much larger reduction in FED. So I'm just going to show you a few more pictures of what it looks like. This is again fixed pre-movement time, looking at the fan case of 120 meters cubed per second. And then at the same time, with the higher fan size, you can see the 10 meter visibility. So the 10 meters of visibility, obviously, is just this little area here, which you'd probably have to be crawling along the floor to be in. Whereas obviously in this, the higher fan size, the visibility is a lot better. Similarly, if we then start looking at the distribution, this is a distribution case at 120 meters cubed, and this is 180 meters cubed per second. So hopefully kept that relatively short. The conclusions, I think, for this specific case study, they may be a bit irrelevant, but in this case study we found that the tenability was most limited by temperature, actually, and fairly early on. But obviously larger fan sizes produce better overall conditions and managed to contain that temperature spread. I think what's more interesting as a wider thought on this is, obviously, I think this really does answer the question, why would you bother doing this when it's a straight tunnel and you can just work it out? Well, actually, this does allow you to see what happens when you put in visibility into your here steps, but could be anything that allows you to put visibility in. You can see the impact, you can calculate the FED. I think it's also interesting to note that really on these things, global parameters don't necessarily give you the whole picture. Just saying that the tunnel can be evacuated in whatever it was, 18 minutes, doesn't really give you much of a picture as to what's actually going on. So you need to drill down and certainly something like STEPS, which is agent-based, you can go and really drill down and find out what each of the agents is going through. And I think it's an interesting question, the use of distributions. What do you get out of them? What's the benefit? It's much easier to assess the difference in fan size if you just look at two fixed cases. It comes up with this is a 20% better or whatever improvement in fan size. But the question is that realistic? Obviously, the second one's much more realistic, the distributions. But then you get into trying to interpret, well, what's fan size, what's distributions, and that kind of stuff. So there's a potted guide. Thank you for listening. Any questions?
Thank you, Henrik.
And don't ask me about FDS, because I'm afraid I can't do
I
that
actually have many questions about this. Actually, me and Steve did a similar study with 6 models, including STEPS, a couple of years ago. So first question is related to my talk. So why did you choose 5 runs? And did you somehow make a convergence study? Or did you make an assessment qualitative? Because what I will do is study the convergence of the standard deviation and at least the standard deviation and the total evacuation time, if not applying some more like advanced method for studying convergence of the curves.
We have, I mean, it's a good question, and I don't actually really have a specific answer to that one. What we tend to find is if we work and do it 5 times and realize that it's pretty much convergent, then we're going to say, yeah, that seems about right. But I have had studies where actually things have been so sort of on a knife edge that actually they're widely divergent, and then you're stuck with the case, well, how many runs do you do? In this case, it was all pretty convergent, so 5, probably a bit of an arbitrary number, but...
Second question, did you look at different, I mean, you used the gene correlation for extinction coefficient versus, but there are different correlations out there. For example, EVAC works with Lund correlation, our equations. Have you thought about the possible impact on using different type of correlations for this?
It's interesting. I mean, to be honest, this is something that whilst we've had the capabilities of doing it, we haven't really done that much of this in actual earnest. This is certainly the first report that I've really seen where this has been put in earnest. So I'm not sure how much research we've done in looking at the different methods or figuring out what the difference is. Certainly we could put them in, but this is just the one that we...
Oh, because in STEPS you had the chance to put custom, I tried it.
Absolutely. I mean, I think this sort of goes back to the question I suppose I sort of raised earlier, is obviously whilst this is based on a client that I can't mention, obviously the client was just interested in the answer and wasn't necessarily interested in us spending sort of lots of time doing, well, what happens if we use this distribution, what happens if we, that for us is all sort of cost, but certainly we could put it in there. So.
And the final question, the curve itself that you use is not the only variable. The interpretation of that curve, if you use it as a fraction or an absolute curve, makes the difference. Me and Steve, we have been looking at how to interpret death correlations and how to interpret the equations, and we saw that models using the same curves, like STEPS and Exodus, can give different results. So this is something that at least should be like a warning for you, because from research we did some sort of sensitivity analysis to see Exodus, he ran this Exodus, and I ran STEPS.
But I think, so I actually think this sort of asks another question, which is sort of underlining essentially what you were discussing earlier, is I think the way we view pedestrian modelling certainly is not to give you an absolute number. It's to do with comparisons. So we run the model with the same assumptions, just different fan size. Therefore, what you should theoretically be looking at is the effect of the difference in fan size. And I'm not saying that it's not insignificant, the fact that you will get a difference in walking speeds because of the different interpretations. But essentially because everything within STEPS is constant, you end up being able to look at the percentage difference. So I never like giving an answer, this is how long it will take, because I can never guarantee that.
But this can be long or short.
But it's exactly, I can say, well, this is going to be theoretically 20% difference, rather than saying, and that sort of goes back to that when you do the static calculation, as we tend to try to do anyway, you've got to have some kind of is 15 minutes a reasonable time, or should it be 5? So it gives you that sort of sanity check. But yeah, for my feeling is, as long as everything is sort of constant within these within these comparative cases, then you're kind of fine.
Thank you.
When you found that the limiting factor for tenability was temperature, were there any other considerations you made, such as tunnel absorption and reflectivity?
I'm going to say for this little case study that we didn't know. In fact, actually, in the real case study that we did, the temperature wasn't the limiting factor. So for our case study here, we just sort of did it as an overall little test case. So yes, I think it would require much more. If this were not just for this presentation, then we would have taken it the next stage, because I was a bit concerned by the temperature. So I think we would have looked at certainly, one of the other things I think that's interesting about this is once you've sort of gone through this run once, you realise, well, temperature is a factor at about sort of 4 to 5 minutes. Well, the pre-movement time we stuck in there was 5 minutes. Surely someone by that point might have noticed that they were getting a bit hot. So I think you'd probably do this circuit a few times if you're going to do this properly.
Any other questions? Okay.
Yes. Hello. My name is Lesba. I have to influence of Okay. Excuse me.
Stand up.
Did you include the influence of the slope of the tunnel in the FDS calculations?
Yes. Yes.
Okay, it was included. I thought in your second slide, I saw those funny pre-movement time. It seems that pre-movement time tends to be normal. Why don't you have?
Yeah, no. I mean, it should be log normal. We could have put a log normal curve in there for simplicity, and for the study, we've put it in as a triangle.
Okay.
Again, I think it comes down to if you're doing these things comparatively, these things they're not irrelevant, but you're always comparing like with like.
Yes, and then the last. Of the distributions, so we have one figure. Why is the output not in terms of distributions?
It is, that's an excellent question. For what we did for the studies, we didn't. I would have to say, if we were going to again take this further, then I would have looked at more of the distribution of outputs. I agree. If you're going to put distributions in, you should really get distributions out. But again, the limitations of what we did. Again, it sort of comes down to clients wanting an answer as quickly as possible. So I would certainly take this longer. I would also have to say that actually I'd like to improve the software capabilities as well, so that we can do more with the software in terms of getting these metrics out.